Hello and welcome. For the next portion of our course, we'll be interpreting and applying the derivative within a variety of contexts. Section 3.7 from Stewart's textbook is an introduction to the wide variety of applications we have for the abstract idea of the derivative. The section is titled Rates of Change in the Natural and Social Sciences, and Stewart goes over a variety of examples for interpretations that we have for the derivative amongst a variety of different sciences. And it's interesting to read over those in the book. And in your future courses, depending on what field you happen to be going into, you might expect to see the derivative show up in your future as well. I would like for you to be able to recognize when you would be in a situation such that the derivative would be applicable. That is, if you are dealing with functions that vary with respect to some input or multiple inputs, as the case may be, and where the functions change in a way that is not constant. If it's a constant rate of change, then it's simply just a linear model, and you could calculate the change in y over change in x between any two data points, and it would be exactly the same. The derivative becomes useful when that rate of change is not necessarily constant, though. So we'll be looking at some applications here and some interpretations of that derivative. So far, we've really talked about the derivative with respect to the idea of where it was originally derived through, Isaac Newton's study to try and use a position function and relate it to a velocity function and then to an acceleration function within the context of trying to describe the force of gravity. We can physically visualize these situations. We can, we can see objects as they fall to the ground, and we can measure their positions and measure their velocities. For instance, we can plot graphs of their trajectories. But there are many other applications out there whereby we're not necessarily talking about physical objects when they are in motion, but the ideas of calculus still apply. And there are also times when we don't see the objects as they are in motion, but we sense that they are in motion, such as the case, for example, with electrical current, where we can measure that there is a quantified amount of charge that is moving, just as we might visualize water moving in a stream or a river, for example. The amount of charge in an electrical current, the amount of charge that travels through a surface in a unit of time, would be an interpretation for the electrical current. Okay, so the more charge in that flows through a surface in a smaller amount of time would indicate a greater current, for example. But there are other more abstract ideas where we can apply the derivative. Okay, so we want to recognize in this section how to apply and interpret the derivative in a variety of contexts and fields of study. The dy over dx, Leibniz notation for the derivative of a variable function y of a single input variable x, we have defined as the limit as delta x goes to 0 of the difference quotient delta y over delta x. Stewart summarizes the many interpretations for this idea of the derivative pretty well here in the book, so I'd like to take a look at this, read this together. So, velocity, density, current, power, and temperature gradient in physics. Okay. We've studied velocity. Density is the amount of mass per unit of space. So in a single dimension, the mass per distance. In 2 dimensions, mass per area would be density. In 3 dimensions, mass per volume would be the density. Okay. When the quantity of mass changes with respect to the spatial input component, okay, then we have a variable density on an object. I'll try and visualize this. Visualization helps when we can do so. If we can imagine just in 1 dimension, let's say we have a wire, right? We'll just say it's a very, very thin wire. let's say I'll try to represent what the mass is on this wire by different amounts of shading. Let's say that on this side, okay, the mass is, not, there's not as much mass, for instance, on this segment right here as maybe there is on this segment right here, so I'll make it a little bit darker over here. So the mass is now increased. And then let's say that the mass increases even further, so I'll try to make it even more solid. Okay, and then maybe I'll go to an even darker color at that point, a darker shade of red, to say, oh, but it's now even more massive. All right. So if we were to take equal size segments of this wire, right, whatever this unit of length is right here, if it were the same as this, and same as this, okay, well, we see that this unit of length of the wire right here has more mass in it than this one did, or any of the other. Okay, so we have mass, okay, per unit of, in this, say, in this one-dimensional, for this one-dimensional object per unit distance, okay, here that mass increases, okay, as we move to the right, okay. Then as a result of that, okay, therefore the density varies as well. Okay. With respect to, let's say, the length, okay, measured from the left edge. So let's say we took the amount of mass on this segment right here, call that M, call it M1, and divide it by the length of the segment, I'll call that D1. Okay, that would give us the density of this region right here. Well, if we then took, let's say, the mass, the total mass, that is, of all of these regions right here, knowing that this one is more massive than that segment was of the same size, and this one was more massive than each of those, and this was more massive than each of those, if we take that mass right there, let's call that M2, and divide it by that total distance, this ratio, which is density for this region here, is not the same as this ratio right here, right? In other words, the density varies. Okay, so the density varies depending on, if we mark the left edge to wherever, to whatever point to the right that we choose to stop making the measurement of mass. Right? So we have a variable density. Well, if we calculate the change in the mass, if we take delta M and divide that by, say, delta D, okay, that would tell us an average, okay, an average density. And we usually use, for the density function, we'll usually use the Greek symbol rho, okay, which looks like a curved P. So that would be like an average density. And then if we take the limit of this as the delta D approaches 0, okay, on a variable function, okay, that would be a derivative. And we can interpret this as a function of the distance we select as the instantaneous rate of change. In this case, since we're doing this in just one dimension, we're gonna call this the linear density function. Okay. This is useful for us to find, for instance, the center of mass of an object. The center of mass can be defined where we would have the same amount of mass to the left and the right. Well, if the object has a uniform density on it, then we would just take the center of the object. But of course, when we have more mass, in this case more mass to the right and less mass to the left, then the center of mass would have to be more to the right. And we could find the center of mass by being able, first we need to be able to determine the total mass of the rod, which, if it is varying continuously along the length of the rod, we would want to add up the masses among a whole bunch of little segments of the rod. That would need to be done but through use of an integral, which we can look at later in the course and in your future courses as well. Okay, center of mass has a variety of applications as well. Electrical current is the rate at which charge moves through a surface. Okay. Visualize that. Imagine this is a wire and there is flowing charge through the wire, and then there is some maybe invisible membrane here through which the charges flow, just as we can visualize the water current through a pipe, or even in a river, for instance. The amount of charge that flows through this surface, okay, per unit of time, and that is the change in the charge with respect to a change in time, okay, would be the average current. And then if we take the limit as the change in time approaches 0, okay, that would be the derivative of the total charge with respect to time, and that is what we call the current, the electrical current. Power is the instantaneous rate of change of work with respect to time. Work is the transfer of energy, okay, the amount of energy that is transferred. So if you take the amount of energy transferred per unit of time, you get the amount of power. Okay? Temperature gradient in physics, a gradient is the direction of greatest increase for a function. You can study that in a multivariable calculus course. And continuing onwards, the rate of a reaction and compressibility in chemistry, the rate of growth, such as for a population, and blood velocity gradient in biology, the marginal cost and marginal profit in economics. Marginal cost is the function that predicts the cost for producing one more unit when you have a variable cost function. So if you imagine the cost, if we know the cost to produce 1,000 units, and if we know the cost to produce 1,001 units, the difference between those would be the actual cost of producing the 1,001st unit. Well, if we have a variable cost function, C of x, where x is the number of units produced, and C is the cost for producing x units, the derivative of that cost function with respect to the number of units that are produced would be a predictor for the cost of producing the x plus first unit. Okay, if you can imagine that. Okay, so we have a function that is not a function of time, but is instead going to be a function of the number of units that are being produced. And this is under the assumption that it doesn't cost the same amount to produce every unit that we produce. For a variety of reasons, we could have that it might be more expensive to produce the first unit than it is to produce, let's say, the 100th unit, and than it is to produce the 1,000th unit. Okay, so you might have a variable cost function, and the marginal cost, the derivative of that cost function, would be a predictor for how much it is going, how fast the cost is changing at that production level. Marginal profit, very similar very similar construct as the marginal cost function, but on a profit function instead, where profit is revenue minus cost. The rate of heat flow in geology, okay, the heat equation uses differential equations. Okay. The rate of improvement of performance in psychology. The rate of spread of a rumor in sociology. Stewart gets into more detail for a variety of these within this section of the textbook. And if you're interested in any of these, I urge you to take a look at some of those interpretations as well. And in the future, again, in your future courses, you may run into the use of a derivative, okay, for a variety of applications. These are all special cases of a single mathematical concept, the derivative. And this is an illustration of the fact that part of the power of mathematics lies in the abstractness of the math. So if we were to just talk about this within the construct of graphs, of parabolas and polynomials, for instance, and only talk about it within the constraints of physics, okay, we would lose sight of the bigger picture, that there's a reason why we want to talk about the derivative as an abstract idea, and that is where it becomes more powerful, that it can be applied in so many different fields. Going a little further, okay, a geologist interested in knowing the rate at which an intruded body of molten rock cools by conduction of heat into surrounding rocks. So if we're measuring the amount of heat with respect to time. An engineer wants to know the rate at which water flows into or out of a reservoir, similar to an electrical current. Okay, the amount of water, let's say the mass of water per unit of time. An urban geographer is interested in the rate of change of the population density in a city as the distance from the city's center increases. So let's say we move outward in 2 dimensions from the city center, and we get different measures of the population within that ring. So if this is the city center right here, and then we say, well, if we are within, this region here, right? What is the population density? That is, how much population do we have per unit of area here? And then if we were to increase the distance from the city center, okay, to a larger concentric circle, okay. So now what is the population? Okay, the total population per unit of area, let's say per square mile. Okay, and furthermore, how has it changed? Okay, and how can the derivative be used to predict the rate at which this population density is in fact changing? It's a similar idea mathematically to the linear density model, except it is no longer per unit of distance itself, but it's instead per unit of area, because we're now moving in 2 dimensions outward. A meteorologist concerned with the rate of change of atmospheric pressure with respect to height. So if we measured the atmospheric pressure, okay, where the input is not time, but if the input was the height or the altitude, right, above the surface, okay, we could measure how fast it is changing with respect to a change in height. In psychology, those interested in learning theory study the so-called learning curve, which graphs the performance, P of t, of someone learning a skill as a function of the training time t. So this could be used to effectively optimize the amount of training time, okay, to prescribe for an individual when you're trying to increase their performance. So it may be that there's too much training time, right? There may be a peak amount of performance that can be reached, okay, for an optimal amount of training time. Okay. In sociology, differential calculus is used in analyzing the spread of rumors or innovations or fads or fashions. Okay. So if P of t denotes the proportion or percentage of a population that knows a rumor by time t, okay, then the derivative represents how fast the rumor is spreading, or how fast the fad or the fashion, okay, is actually spreading through the population as well. Okay. Right, so these are all potential applications we have for the derivative as a construct. Okay. For your assignment, we'll be focusing mainly on applications within physics and some general interpretations as well of the derivative. Okay. So I've included some typed lecture notes for you as well. Okay. Starting with a discussion again of the position function related to the velocity and the acceleration function, with the inclusion of this notion of finding the distance traveled, okay, over a given time interval. And I want to distinguish between displacement and distance here at the start. Displacement can be thought of as over a time interval from t1 to t2. Displacement is how far the object is at the end of the time interval versus where it was at the beginning of the time interval. So the difference in the positions, simply. Okay. Now, that's only the same as distance traveled if the object was moving in one direction, okay, from the starting point to the ending point. But if the object instead moves back and forth, okay, over that time interval, then these two are not going to be the same as each other. Consider the following example. Imagine a person that is pacing back and forth in a hallway a few times. So they're just walking along a straight line, back and forth and back and forth, okay? And this schematic here is a helpful way to try to visualize this back and forth motion. But the object is not actually moving up, okay, or north, Okay, it's actually the object is moving really along the line. So we can really envision that this particle or this person is really just going back and forth right along this line right here. Okay, but this is the path that they follow. So they started at this position right here where t is equal to 0, the initial position. They walked forward. Let's say that to the right is forward, right? They walk forward, then they turn around, they go backward, and then they go forward again, and then they go backward again. By the time, let's say 6 seconds has passed, when t is equal to 6, they are back at the same position they started at, right? They just went back and forth, back and forth. So what is the displacement for the individual over the first 6 seconds then? Well, they started at this position. 6 seconds later, they're right back at the same position. So the displacement would be 0. There's no change in their position over that 6 seconds from the beginning to the end. But is that the same as the distance they traveled? No, because they did travel a distance. They didn't, right? Their displacement was 0, but the distance they traveled should clearly be a positive amount. Right? First they traveled out to the right to this point right here, whatever their position is here, versus their starting position, they've traveled that distance. Well, if this is s is equal to 0, where s is position, and this is s equals 1, then over the first second, they've traveled 1 unit of distance already. Okay? Then, as they travel back towards the left, from this location here on this line back to here, from s equals 1 back to s equals -1, they have traveled now an additional 2 units of distance. Okay, so by the time 3 seconds has passed, they have traveled how far? They've traveled 1 unit of distance this way, plus 2 units of distance this way, for a total of 3 units of distance of travel. Now their displacement at t equals 3, okay, would be the difference between their final position and their starting position. That is, their displacement is -1. Right? They are, in other words, 1 unit of distance to the left of their starting point, hence the negative. Okay? But the distance they traveled, if we don't allow distance to be negative here, okay, the total distance they would have traveled, okay, in the first 3 seconds turns out would have been a total of 3 units of distance. Okay, so we can continue to find the total distance traveled, okay, during some given time interval, let's say from 0 to 6 in this case. If we wanted to do that, we would want to find the magnitudes of the displacements on a variety of different segments. So clearly displacement and distance are not necessarily equal to each other. Again, they would be equal to each other if this was all in one direction. If the person started at t equals 0 and simply traveled to the right for 6 seconds and then stopped, then the displacement would equal the distance that they traveled. So the difference here between distance and displacement, okay, can be visualized and summarized by a change in the direction of travel. And the change in the direction of travel occurs, okay, at points like this point right here, and this point, and this point. Well, if the direction that they're traveling is changing, okay, then the other thing that changes, this is with respect to the derivative now, is the velocity. The velocity along this first segment right here would be a positive quantity, all right, positive velocity. And the velocity over this next segment right here, from t equals 1 to t equals 3, that velocity would be negative because they're moving to the left. Okay? So we have at this point right here, when t is equal to 1, the velocity would equal 0 because we have changed from a positive to a negative velocity, and we have done so in a continuous fashion. Again, the velocity is going to equal 0 at this point because we're going to have a change from a negative velocity to a positive velocity, simply because we're switching from moving to the left, which is where velocity would be negative, to moving to the right, which is where velocity would be positive. And so that change happens when the velocity is equal to 0, as long as we have a nice, smooth, continuous, okay, change from the left to the right. Okay? And again, the velocity would equal 0 here. Okay, so if we are given a formula instead of a picture, if we're given a formula describing the motion of an object, okay, and if it might be moving back and forth, or we don't know if it is, we can analyze whether it happens to move on back and forth on subintervals by locating where the velocity might equal 0, because when the velocity is equal to 0, it might be turning around. Does that mean that when the velocity is equal to 0, it must turn around? Can we imagine a situation where an individual walks to the right, stops, But instead of moving back to the left, what if they start moving back to the right again? Could that happen? Yes, it could. It could be that they just stopped for a moment and then continued moving to the right. Okay, so just finding where the velocity is equal to 0 doesn't guarantee that you have a point where they turned around necessarily, but it does indicate that there's a possibility that they may have turned around, that the object may have started moving in the other direction. Okay? And we're going to want to consider that. Okay, so what was the total distance that the person traveled over the first, let's say, 6 seconds? Well, we would take this distance, which is 1 unit, plus this distance, which is another 2 units, because we take the magnitude or the absolute value, okay, of the difference between these positions, plus another 2 units of distance moving back to the right, plus another 1 unit of distance moving back to the left. So we get 1 plus 2 plus 2 plus 1. So that's 1, 3, 5, 6. So they have traveled 6 units of distance over those 6 seconds. Meanwhile, their displacement is again just equal to 0 over those same 6 seconds. So how do we do this formulaically? We take the interval of time that we're given. Let's say we had the interval from 0 to 6. Okay? And we want to subdivide that interval from 0 to 6, okay, into sub-intervals associated with when the person is not standing still. So we found that the individual from the schematic, okay, the person was standing still when t is equal to 1, t is equal to 3, and t is equal to 5. So the sub-intervals we're going to want to analyze are from 0 to 1, 1 to 3, 3 to 5, and 5 to 6. And again, those sub-intervals are found around values where the velocity would have been equal to 0. Okay? But we are calculating the difference in the position. Okay? And the reason I have absolute value bars around each of these differences here is because we only want to calculate distance as a non-negative quantity. So from using the schematic, we can see the velocity at 1 second must equal 0. And of course, velocity is the first derivative of position. The velocity at 3 seconds must equal 0, and the velocity at 5 seconds must equal 0. So 1, 3, and 5, okay, become important values for us to subdivide our original interval from 0 to 6. So 0 to 1, 1 to 3, 3 to 5, 5 to 6. We calculate the magnitude of the displacement over each of these subintervals. So we find out what is the position at 1 second minus the position at 0 seconds, s of 1 minus s of 0, and take the absolute value of that in case that quantity would have been a negative value. All right, so that distance can always be interpreted as a non-negative value. And we do the same thing for each of these subintervals, and we sum them together, we get the total distance traveled. So let's see how this would have been done formulaically, okay, if we were given a position function, not by use of a schematic, okay, but instead a variable position function. Find the total distance traveled by a particle during the first 6 seconds given this position function here. S of t is t squared e to the negative t. Again, okay, the theory suggests that we should find first when the velocity is equal to 0. At any time when the velocity is equal to 0, there is the potential that the particle is going to turn around. Now, again, it doesn't guarantee that the particle is going to turn around. It could be that it just momentarily stops and then continues in the same direction. But as long as we are sure to take the absolute value of the differences, the absolute value of the displacement, that is, the absolute value of the differences between the starting point and the ending point on that subinterval, it wouldn't matter whether they were going left or they were going to the right. In either case, when we take the absolute value, we're going to be calculating the distance that they traveled over that subinterval. But it's important to find where the velocity is equal to 0 so that we know which subintervals to calculate these displacements over. All right, so how do we find out where the velocity is 0? Well, when we're given a position function, we take the derivative of position. So you take the derivative, this is done by the product rule in this case. You set that equal to 0, solve the resulting equation algebraically. In this case, we can factor out t e to the negative t as the GCF, set each factor and then equal to 0 to find solutions. So either t is equal to 0, or t is equal to 2, or we have this e to the negative t is equal to 0, but that's an exponential, and that exponential can never equal 0, right? E to the negative t is not equal to 0. Okay, it's greater than 0 for all t. So the only solutions here are t is equal to 0 and t is equal to 2. And we're interested in finding the distance they traveled during the first 6 seconds. That is on the interval from 0 to 6, the closed interval 0 to 6. Okay, so t is equal to 0 is already an endpoint to that interval, so we only have to choose t is equal to 2 to subdivide this interval. So we're interested in the displacements, which we're going to take the magnitudes of those displacements on the intervals 0 to 2 and 2 to 6. So we take s of 2 minus s of 0 to find the displacement over the first 2 seconds, the difference in the positions, s of 2 minus s of 0, okay, from the original position function. So plug in 2, plug in 0, take the difference between the two. Take the absolute value in case the quantity was negative. Clearly this one doesn't happen to be negative, but the absolute value there is, again, to say in general you need to take the absolute value, right? And then we take the displacement over the interval from 2 to 6. That's s of 6 minus s of 2. Take the absolute value, just in case it would have been a negative quantity, which in this case, this would have been a negative quantity if we did not take the absolute value. So here it would have been important to do so. So we add up those magnitudes and we get the total distance traveled. Okay. We could also sketch one of those schematics here for this particular one. What would that look like? Well, we have over the interval from 0 to 2, okay, what direction were they traveling? Well, they started at position 0, they were at 0, and at s of 2, their position at 2 was positive 0.541, that many units from 0, and so that's to the right of 0. So let's sketch a little schematic, okay, for this. So the path that they followed. Okay, so we have s of t equals t squared e to the negative t, okay, on 0, 6, okay, and that's from the typed lecture notes. Okay, so we have first at t is equal to 0, the position is equal to 0. Just plug 0 into the function to find that position, right? And then we have at t is equal to 2. So at t equals 2, the position was approximately 0.541. So over the first 2 seconds, okay, this particle was moving to the right. Okay, and then it's standing still. Now, is it going to move back to the left, or is it going to continue moving to the right after momentarily standing still at t is equal to 2? Well, at the next position at s of 6, we have 0.089, right, which is positive, but it is less than 0.541. So we have 0.089, right? Okay, so 0.089. So it comes back to about here. All right. So this is at t is equal to 6. S is approximately 0.089. Okay, so the particle moved back to the left. So we had that the velocity was positive for the first 2 seconds. The velocity was negative for the next 4 seconds. Okay, less distance traveled over the last 4 seconds versus the distance traveled over the first 2 seconds, so the object slowed down as well. Okay. Let's take a look at the homework here. Okay. Many types of questions we could be asked to analyze these functions using the calculus, as well as the use of algebra, trigonometry, for example. Okay. We know how to find the velocity at time t. It's a velocity function. When we are given a position function, a particle moves according to the law of motion s equals f of t, where t is measured in seconds, s in feet. Therefore, we have a position function. S is measured in feet, and t is time. So we have position with respect to time. Therefore, the derivative of this given function f of t with respect to t would be the velocity function. What's the velocity after 1 second? Well, if we have a velocity function, we can plug t is equal to 1 second, okay, into the velocity function. When is the particle at rest? It's at rest if it's not moving. That is, if the velocity is equal to 0. So we set the velocity function equal to 0 and solve for the times t when that would occur. When is the particle moving in the positive direction? Well, if we know when it's at rest, Okay? If we know a value of t when it's at rest, then we also know the values of t when it is not at rest. Right? If we've already solved for when the velocity is equal to 0, then any other values of t that we choose to plug into the velocity function would give us a non-zero value. Right? So we can plug in test values, okay, test values surrounding when the particle is at rest, plug in test values in order to find out when it is either has a positive velocity or a negative velocity. So let's take a look at some analytical questions we could answer using one of these position functions. Let s equals f of t be the position of a particle for t is greater than or equal to 0, where t is in seconds and s is in feet, given f of t equals t over 1 plus t squared. Part A, find the velocity at time t. Since we are given a position function, the output is in feet, the input is in seconds, we can find the velocity function v of t, which would be giving us units in feet per second, by taking the derivative of our position function. So v of t is equal to f prime of t. Let's use the quotient rule here. So we get low times the derivative of the high minus the high times the derivative of the low over the low squared. Okay, so there is a velocity function. Because we're going to be doing lots of things with this, I think it might be helpful to simplify this. So let's see what we can do. 1 plus t squared minus 2t squared would be 1 minus t squared. And then that's over 1 plus t squared quantity squared. So there's our velocity function of time t, for t is greater than or equal to 0. Now we can use this to answer the next question. What is the velocity after 3 seconds? Okay, we can answer that question by inputting 3. Since the unit of time was in seconds, then we are inputting t is equal to 3 into the velocity function. Right? Okay, so this comes back to algebra then. This is not a calculus question. Okay, now at this point we've already done the calculus. So 1 minus 3 squared over 1 plus 3 squared squared. So it's 1 minus 9 is negative 8 over 10 squared is 100. Okay, as a reduced fraction, what's this? Negative 2 over 25, or as a decimal, right, negative 0.08. Okay, what did we just find? The velocity after 3 seconds is negative 0.08. What units? Feet per second. C. When is the particle at rest? How do we interpret that? Well, it's at rest when it is not moving. It is not moving when the velocity is equal to 0. So this is asking us to set the velocity function equal to 0, okay, and solve for t. That make this statement true. Okay. So v of t is equal to this, 1 minus t squared over quantity 1 plus t squared, okay, squared. So we set 1 minus t squared over the quantity 1 plus t squared squared equal to 0. That would answer the question when the particle is at rest. We only want values of t that satisfy this equation that are within the domain where t is greater than or equal to 0. Now the denominator here is always positive. We can multiply both sides of this equation by the denominator and just cancel it out. Okay. Right, there's no discontinuities to be concerned with here, so it's sufficient for us to just say 1 minus t squared is equal to 0. In general, we want to be on the lookout for discontinuities. Right? If the denominator indicated that there were values of t that we weren't allowed to select, we would have to be on the lookout for those as possible extraneous solutions to this equation. Right? That's a concept from algebra that we should recall. Okay, so now we're solving this equation 1 minus t squared is equal to 0. When the numerator is equal to 0, the whole ratio is equal to 0. And that has solutions when t is equal to plus or minus 1, right? You can solve it with a square root property. You can do factoring, set the factors equal to 0. You could even do the quadratic formula if you really wanted to, right? There's multiple ways you could solve this algebraically. But only one of these values of t is actually within the given domain. T is greater than or equal to 0. That's where t is equal to 1. Okay? T is equal to 1, okay, is in the domain. The domain was t is greater than or equal to 0. Okay, so that's the only relevant solution. When is the particle at rest? According to this, okay, the particle is at rest at 1 second. That's 1 second after, after the initial observation was made at 0 seconds, right? D. When is the particle moving in the positive direction? Moving in the positive direction. Well, we know about its motion by examining its velocity. Okay, so this seems to indicate that we want to talk about velocity right now. Okay, we already know when the velocity is equal to 0. That is, we know when it is standing still, or when it is at rest. Since the velocity function is continuous, right? So again, since the velocity is continuous, okay, it can only change direction by coming to a stop, by coming to rest first, right? So, to negate this statement, if we had a velocity function that was not continuous, it would be possible for the for that object, okay, to go from negative to positive without going through 0, right? It's possible to graph something that is negative and then becomes positive if we allow for discontinuities in the graph, right? But if we have a function that is continuous, the only way for a function such as velocity to go from, let's say, negative to positive, to transition from going from one direction to the other, if it is continuous, the only way that is possible is if it crosses through 0, right? If it is continuous, okay? And this function is continuous. How do we know the velocity function is continuous, by the way? Look at it, right? It is built up out of the ratio of continuous functions, okay? The denominator is never equal to 0. The given domain is t is greater than or equal to 0 nonetheless. We know that this is continuous over its entire domain, as we've discussed earlier in this course. Okay, so continuity is helpful to us here. Since the velocity is a continuous function, it can only change direction by coming to rest first. That means that when we are looking at the interval, okay, t is greater than or equal to 0, in other words, from 0 to infinity, okay, we know that this object stands still at t equals 1. So we can split this up into subintervals from 0 to 1. Okay, well, I'm going to leave that open because we know what happens at t equals 1, right? It's certainly not moving to the left or right at 1. That's when it is standing still. And then we can look also on the interval from 1 to infinity. Okay, because it can only change direction by crossing through a value of time where the velocity is 0, then no matter what value we test from within this interval, okay, no matter what value of t we choose between 0 and 1 to test in the function, okay, the behavior, that is the velocity, is going to be similar throughout the entire interval. So for instance, if we choose t is equal to 1/2 and plug that into the velocity function, let's say we did that, v of 0.5. If this comes out to be a positive number, then it must have been positive velocity throughout the entire interval. Not a constant velocity, but it must have been positive throughout the entire interval. If this comes out to be a negative quantity, okay, indicating it had negative velocity or moving to the left, then it must have been a negative velocity throughout the entire interval. Not a constant velocity, but it must have been all in the same direction throughout the entire interval, because there's no way for it to switch from going left to right unless it crossed through a point, okay, where it was standing still. Okay, and so we're also going to want to test in here. Why is it not sufficient to just test 1? Let's say we find out that it is moving to the right, or it is in the positive direction in this interval. Does that guarantee that it has to be moving to the left over here? No, just because when it comes to stand still, when it's at rest instantaneously, it could just be standing still momentarily and then continuing onward to the right. So it could be that it's moving in the positive direction within both of these intervals, but not at t equals 1. Or it could be that it is not moving to the right in either of these intervals. In any case, we need to test within both of these intervals. So I'll test, for instance, let's say 0.5. Okay, we could even test 0, right, which would be a much easier value for us to test. But no matter which value we choose within this subinterval right here, okay, we're going to get the same characteristic velocity throughout the entire interval. Okay, so plugging 0.5 into the velocity function, 1.1 minus 0.5 squared over 1 plus 0.5 squared quantity squared. Now all we really want to know here is when the velocity is positive. We want to know when v of t is in fact greater than 0, not equal to 0, but when is it greater than 0, because that indicates that the particle is moving to the right, okay, when that occurs. Okay. So we're only interested really in the sign here. Well, the denominator is, well, we got a square of a real number is positive, we're adding a real number that's positive, and then we're squaring a real number that's positive, so the denominator is certainly positive. What about the numerator? Okay, well, 0.5 squared is 0.25. Okay, 1 minus 0.25 is positive, so we have a positive divided by positive, okay, which ultimately gives us a positive quantity. Therefore, the velocity at 0.5 is greater than 0. Therefore, the velocity is greater than 0 throughout this entire interval. Okay. What about testing in here from 1 to infinity? For instance, what if we choose a value like 2? Well, v of 2 is 1 minus 2 squared over 1 plus 2 squared. Okay, that quantity squared. Again, the denominator is strictly positive. We can see that. And the numerator, well, that's 1 minus 4, which is negative. So we have a negative divided by a positive, which is negative. So the velocity is less than 0 from 1 to infinity. So the path that this particle takes, it seems, it starts out for the first 1 second over the interval from 0 to 1, it is moving to the right, and then from 1, and then after 1 second onward for the rest of all time, it is moving then to the left. Okay. So the particle moves to the left, the particle moves to the right. Okay. On the interval closed at 0, open at 1. Okay, so that was part D. Part E. Find the total distance, okay, the total distance that the particle traveled, okay, during the first 8 seconds. Okay. All right, so again, it's important to consider when it is potentially changing in direction, and we just investigated that. Okay, so on the interval from 0 to 8, okay, we're going to split that up into the subintervals from 0 to 1, okay, and 1 to 8. Okay. Right, because v of 1 is equal to 0. It's the only time on this interval from 0 to 8 where the velocity was equal to 0. And then we're going to take the magnitudes of the displacements over these subintervals. So s of 1 minus s of 0, okay, take the absolute value of that difference. Okay, that's the magnitude of a displacement, plus the magnitude of the displacement, okay, over the interval from 1 to 8. So s of 8 minus s of 1, take the absolute value of that difference right there. Okay, we need to calculate these quantities then. So let's find out. So we have back to the position function now, the original position function, right, which was t over 1 plus t squared. Okay, so we have s of 1, which is f of 1, is 1 over 1 plus 1 squared. Okay, and that equals, well, 1/2, right? What about s of 0? S of 0 is equal to, well, 0 over 1 plus 0 squared. Okay, so that equals 0. Okay, so we have s of 1 minus s of 0. Okay, so that's the absolute value of 1/2 minus 0. Right, the absolute value is not necessary there because it's already positive. okay, but it ensures that our result is going to be non-negative, right? S of 8 is equal to 8 over 1 plus 8 squared, all right? So that's 8 over 65, okay? And finally, we already have S of 1, again, is equal to 1/2, right? Okay, so S of 8 is 8 over 65, which we'll note is less than a half, because a half would be 32.5 out of 65. Right? 8 over 65 minus 1/2. So this would be a negative quantity, so the absolute value would be necessary in this case. So we have 1/2 plus, now what is this equal to? We have 8 over 65, okay, minus 1/2. Okay, so let's get a common denominator here. So you can get 16 over 130 minus 65 over 130. Okay, so this is 1/2 plus 65 minus 16 is 49. So this is going to be positive 49 over 130 because I've already taken the absolute value here now. Okay, so add that to 1/2, which is 65 over 130, and 65 and 49, okay, is 159, 114 over 130, right, reduces to 57 over 65. Okay, so 57 over 65 feet. Okay, 57 65ths of a foot. Okay. Okay, over the interval 0 to 8. Okay, in other words, the first 8 seconds of travel. Okay. So that was part E. Part F, how about a schematic? Okay, schematic diagram. To illustrate the motion, right? The way it says it in your homework. Let's see, how's the homework say? Draw a diagram like this figure to illustrate the motion of the particle. Here we are again, WebAssign, giving graphs where it's multiple choice, okay? But we should be able to construct these graphs if we are not already shown what the answers are supposed to be, right? So sketch a schematic diagram to illustrate the motion of the particle. Okay, so we have it started at when time is equal to 0. Okay, the position was also 0. So let's start there. Okay, t is equal to 0, s was equal to 0. Is it always going to start at position is equal to 0? No. This one happens to start at position equal to 0, and so did the previous exercise. But just to note, it doesn't mean you always start at position is equal to 0. When time is equal to 0, it depends on the actual position function, right? We see by plugging in t is equal to 0, we get the position is equal to 0 for this particular model. Okay, so it starts at t is equal to 0. Okay, and then okay, it travels to the right. We found it travels to the right, okay, on the interval 0 to 1. And when it gets to time is equal to 1, the position becomes 1/2. Okay, so this is going to move to the right to, right, for when t is equal to 1, the position is equal to 1/2. Okay, so the particle is moving to the right like this, and at t is equal to 1 is where it stops, so we're going to indicate it like that. It's actually moving right along the line, and then it's turning around and going back the other direction. Okay, but we're showing that motion off the line up here. Right, the arrows indicate its direction of travel was to the right, okay, during the time interval from 0 to 1, and the space interval from 0 to 1/2. Okay, then it turns around, and for the remainder of all time, 1 to infinity, it continues back to the left. Now we know what position it's at after 8 seconds. Its position after 8 seconds is 8/65, okay, of a foot to the right of 0, right? So 8/65 is is about 1/8, right? A little bit less than 1/8. Okay, so pretty close to 0, but not quite at 0. So let's say it's like here, 8 over 65. Okay, so we know that it's going to get to like this position right here, right, after 8 seconds. Okay, and that's the position where s is equal to 8 over 65, and it was traveling to the left. But it continues traveling to the left for all time, so it just continues moving in this direction. Okay, so here would be a schematic for this particular model then. Okay, let's move ahead to, let's see, part G. When is the particle speeding up? Okay, and follow that up with when is the particle slowing down? What does this reference? We know the speed that it is traveling, that is the velocity, the magnitude of the velocity tells us the speed, but how do we interpret when the magnitude of the speed is increasing? Now, the difference between velocity and speed is that velocity also includes the component of direction. Okay, and the change in the velocity is the acceleration. When we consider, that we need an acceleration function then. Okay, we need to find out how the velocity is changing. Okay. Now, furthermore, how do we interpret acceleration with respect to velocity to determine when the object is speeding up? That is, if the acceleration is positive, does that mean the object is necessarily getting faster? That depends on what direction the object happens to be traveling. Let's go back to the type notes. So I tried explaining this concept here in this example as well. Okay. Consider that a car is accelerating forward by increasing its already positive velocity, for example. Right? So if you're already traveling forward and then your acceleration is positive, right, then you are going to be traveling faster in the forward direction. That would be an acceleration. But what if you were traveling backwards? If you're traveling backwards, then you would already have a negative velocity. To accelerate backwards, if you put the car in reverse, if you wanted to accelerate backwards, right, then you would want to, right, then you would want to decrease what is already a negative velocity, right? So if you're traveling backwards at, let's say, negative 5 miles per hour, and you wanted to accelerate backwards to negative 10 miles per hour, right? And that means that you want an even greater negative velocity. You would not want the acceleration to be positive in that case, because you're trying to get a larger negative velocity out of it. So speeding up is either an increase in an already positive velocity, that's forward and then going forward even faster, or a decrease in an already negative velocity. That's if you were already going backwards and you wanted to go backwards even faster. Okay, this example here, okay, represents this idea by use of a graph. If we have a graph of not the position, but the graph of the velocity itself, right? So if a point on this graph, if the y-coordinate of a point on this graph tells us the velocity, for instance, but as we read this graph to the right, that's where time is increasing. So we see, like, along this first segment right here from 0 to 2, right, the velocity started out as positive and it approached a velocity of 0. Okay, was the object, okay, accelerating or decelerating, okay, over that interval of time from 0 to 2? Well, it started as a positive velocity and went to 0. Imagine an object that is moving forward because its velocity is positive, and then over time comes to a stop. It would have decelerated, right? Okay, so it would have slowed down. Now what happens? Now the object starts traveling backwards, right? At a point like this one right here, it already has a negative velocity. They are now traveling backwards, albeit slowly backwards. But then they are going to be traveling now at a more and more negative velocity, okay, up until where t is equal to 3. That is, their velocity, okay, is becoming more and more negative. Imagine the vehicle is now traveling backwards at a faster and faster rate along this interval. Even though acceleration itself, being the rate of change of velocity, the acceleration over this interval from 2 to 3 is a negative number. Nonetheless, because velocity was negative, okay, along with acceleration being negative, since both of them were negative, this really does indicate that the object was accelerating, okay? it was accelerating over the interval from 2 to 3 seconds. Okay, and then from 3 to 4 seconds, what happens? We see the graph of the velocity is returning back towards 0. That is, we now have, again, negative velocities, so the object is still moving backwards along this interval, because for any point that we choose off of this graph, the associated value of v is negative. So the object itself is actually traveling backwards when we're at a point like this. But the velocity is getting closer and closer to 0. In other words, the object is coming to a stop again. Okay, so if we were to try to plot, the path that this travels, it would be in motion. We would need a video in order to do that. We have an object that starts out at a faster rate, moving to the right. Okay, it's moving to the right, and then it continues to move to the right until t is equal to 2 seconds, but it slows down and then comes to a stop at t is equal to 2. Then at t is equal to 2, it starts moving backwards, and it starts to accelerate backwards until t is equal to 3. Okay, and then from t is equal to 3 to t is equal to 4, it's still moving backwards, but it's slowing down as it's moving backwards. So we have an object that moves to the right and comes to a stop, and then speeds up a little bit as it goes back to the left, and then slows down and comes to a stop as it goes to the left as well. So speeding up, okay, when comparing velocity and acceleration, speeding up can be indicated by when the velocity and acceleration have the same sign. If they are both positive, then the object is speeding up. If velocity and acceleration are both negative, then the object is also speeding up. Okay, it's not enough just to look at the acceleration by itself, and that's the point. So if we want to know when this particle is speeding up, we need a of t, okay, and the object is speeding up when a of t and v of t, okay, have the same sign. Okay, so that's important. Consider that conceptually. I hope you can visualize this. Okay, a car that is accelerating forward versus a car that is accelerating backwards. Okay, let's add a new layer here. Let's find our acceleration function, right? That acceleration is the derivative of velocity. Okay, so let's take our velocity function, this 1 minus t squared over the quantity 1 plus t squared squared. Okay, and we're going to need the derivative of that. All right. So a of t is equal to v prime of t, right, which is the first derivative of this 1 minus t squared over the quantity 1 plus t squared squared. Okay. All right, so now we're going to need a quotient rule, and there's also going to be a chain rule in there. Okay, so starting with low, 1 plus t squared squared, d high, that gives negative 2t, okay, plus the high, 1 minus t squared times d low, okay, which is going to be what? 2 times the quantity 1 plus t squared to the power of 1. Right, so that's the general power rule there. And then the chain rule is we need the derivative of the inner function, and that is 2t. Right, so that's a 1 and not a prime there, just to indicate that I'm remembering the power rule. Okay. Sometimes we forget that. Like if this was a 3, sometimes I see where the 3 goes out here, but then we forget to write that there's a 2 out there. So I just wanted to be clear that we completed the general power rule there. So we have low d high, okay. Speaking of errors, okay, typos, low d high minus high d low, okay, over the lower function, which then is squared. Okay, we got some simplifying to do here, right? Let's see. Let's do some factoring. We've got a negative 2t, we got a 1 plus 2t, 1 plus t squared quantity squared over here. I got a 1 plus t squared right here, so I got a 1 plus t squared here, I got a 1 plus t squared here I can factor out. I also have a negative 2t along with a negative 2t right here. I'm going to take that out. So negative 2t and 1 plus t squared, and then I'll open up a bracket. I'm going to be left with an additional 1 plus t squared from this group right here. Okay, I've taken out the minus. Okay, so that becomes a plus. We still have this 2 hanging out. We still have this 1 minus t squared, and we took out that 1 plus t squared right there. Okay, and the denominator is 1 plus t squared quantity to the power of 4. Continuing to simplify them. So we have negative 2t right here. We have a 1 plus t squared. We have 1 plus t squared to the power of 4. So I'm going to get to cancel one of those with one of these. So that leaves a 1 plus t squared cubed. Okay. In brackets, what do we have? 1 plus t squared plus 2 minus 2t squared. Okay, so we have 1 plus 2 gives us a 3, and then we get t squared minus 2t squared leaves us with a minus t squared. Okay, so that seems reasonably simplified right there. There's our acceleration function. We could continue to play around with it from there. We could distribute that if we wanted to, but this is reasonably simplified right here. Right? So we want to know when the acceleration and velocity are positive. That is, if the acceleration is greater than 0 and the velocity is greater than 0, okay, then that would indicate that it is speeding up. Okay. If the acceleration is less than 0 and the velocity is less than 0 simultaneously, that would also indicate that it is speeding up. So I'd like to know when the acceleration is positive, when the acceleration is negative. And we can find out when it is positive versus negative on a continuous function by locating when is the acceleration equal to 0. And once we know when it's equal to 0, we can then use test values within the subintervals around it, like we did with velocity, in order to find out when the acceleration is either positive or negative. Okay, and we really only need to consider this where t is greater than or equal to 0, the same domain as we started with the position function. Okay, so when is it equal to 0? Well, we set our function equal to 0. Okay, the denominator is always going to be positive. We can multiply both sides by the denominator. Okay, and then we're just left with solving when the numerator then is equal to 0, and that happens when t is equal to 0 and when t is equal to plus or minus the square root of 3. But on the interval from t is greater than or equal to 0, okay, we're only going to take where t is equal to 0 and t is equal to the principal square root of 3. Okay, because t is greater than or equal to 0. So that's when the acceleration is equal to 0. Okay? Okay, so we should consider the intervals then from 0 to root 3 open, right? The open interval from 0 to root 3 and from root 3 to infinity then. And let's choose test values in here. Well, root 3 is about 1.73. So we'll choose a value between 0 and root 3 like, test in here. Let's take t is equal to 1. Okay, and then we're also going to want to test in here. Okay, like say we'll take t is equal to 2 because that's greater than the square root of 3. And where we're testing it is in the acceleration function. Okay. Let's test a of 1. Okay. Here's our acceleration function. Negative 2 times t times 3 minus t squared over 1 plus t squared cubed. Okay, so the denominator is positive, of course. Right, this particular denominator is positive for all real numbers. The numerator is, we have a negative times a positive. Right, we have a negative times a positive. And 3 minus 1 is positive. So we get negative divided by positive, which is negative. Okay? All right, so we have a of t is less than 0 on the interval that we just tested. That is the interval from 0 to root 3. Now test at 2. A of 2 is equal to negative 2 times 2 times 3 minus 2 squared over 1 plus 2 squared cubed. Try to clean that up a little bit there. Again, the denominator is positive for all real numbers. The numerator, we now have a negative times a positive times a negative, right? 3 minus 2 squared, right? That's going to be a negative. So we have positive over positive, which is positive. So we have found that the acceleration is greater than 0 on the interval from root 3 to infinity. So we can compare acceleration to velocity on intervals where neither of them happen to equal 0. Let's take a look at some intervals. Right, so we have velocity was equal to 0. Right. At what value? Velocity was equal to 0 at 1. So v of 1 is equal to 0. We have acceleration was equal to 0 at root 3. Okay, and we have that t is greater than or equal to 0. So some intervals of interest would be from 0 to 1. Okay, and then from 1 to root 3. And from root 3 to infinity. And within each of those intervals, let's see, we'll choose a value of t that we could select. So for instance, between 0 and 1, we could take 0.5. Between 1 and root 3, we could take 1.5. And between root 3 and infinity, something like 2. But any test value that we might want to select. And then we can see, well, what is the associated velocity with respect to time? And I only want to know whether it's positive or negative, and that's it. And similarly for the acceleration with respect to time. Okay. So for instance, on the interval from 0 to 1, we found that the velocity was positive on that interval. We did that work previously. And the acceleration, well, acceleration we found, right, here we go. Right, we found that the acceleration was negative from 0 to root 3. Okay, so the acceleration is already negative from 0 to 1. So they are different signs here. Okay, how about from 1 to root 3? At a place like something like 1.5, for instance. Well, we already have that that the acceleration is still negative there. Right, we've already determined that. We need to figure out then what is the velocity at 1.5. Okay. Back to our previous work here. Okay. We established that the velocity was positive from 0 to 1, and then the velocity became negative from 1 to infinity. Okay, so at a place like at a time value such as 1.5, the velocity was negative there. So here we have that both velocity and acceleration are negative. So we have that it is speeding up, okay, on the interval from 1 to root 3. Testing at a value like 2, again, the velocity is negative on 1 to infinity. Okay, and the acceleration becomes positive from root 3 to infinity. So there are opposite signs there. Okay. So we have that the particle is slowing down on the other two intervals. In this interval, right, we have different signs. So slowing down. Okay, here we go. It is slowing down on the interval from 0 to 1, and it is slowing down on the interval from root 3 to infinity. Okay, so that completes our analysis for where it is speeding up and slowing down by comparing values of the velocity to the acceleration. Okay, on intervals where neither of them were equal to 0. Okay, so we want to see when velocity and acceleration have the same sign, then the particle is speeding up. When they have opposite signs, then the particle would be slowing down. So let's take a look at some other types of questions you might see in your homework. What else? Okay, sketching graphs of the associated functions. This one, this example has a cosine curve. You should be able to sketch a basic cosine curve, and of course the derivative of cosine would be negative sine. And I need to use a chain rule here when finding the velocity. To sketch the velocity curve, you need to be able to sketch a sine wave. Okay, and then to find the acceleration. Okay. The acceleration, you would need to find the derivative of velocity, so the derivative of the sine. So you're going to get back to a cosine model. So you have to be able to graph those three, okay, to compare them to each other. When is it speeding up? When is it slowing down? You can also do a graphical analysis. Again, the idea is the particle is going to be speeding up when the acceleration and velocity have the same sign. Okay, so you can take a look at a velocity. I'm not saying that this is the answer, but suppose that this was the correct graph. the velocity curve on this interval here from 0 to 3 would indicate that the velocity is negative from 0 to 3. Meanwhile, the acceleration is negative, not from 0 to 3, but from about 0 to 1.5. So we would have that the velocity and acceleration are both negative from 0 to 1.5, indicating, since both of them are the same sign, indicating the particle would be speeding up from 0 to 1.5. Furthermore, we could say since the velocity is negative, that this object is actually moving to the left. It's speeding up to the left from 0 to 1.5. Notice we can also see that when the acceleration is equal to 0, what happens to the velocity curve? When the acceleration is equal to 0, the velocity curve, which is nice and smooth, would have a horizontal tangent line. It would, in this case, approach a minimum. Right? Now, while on the interval between 1.5 and 3, where the velocity is negative, the associated acceleration on that same interval is positive. They're opposite signs. But then let's say, from 3 to 4.5, if this were the correct graph, from 3 to 4.5, we have the velocity is positive and the acceleration is positive, indicating that it is speeding up and moving to the right on that interval then. Okay? So that's how you could tell where it's speeding up. And when is it slowing down? On intervals where the velocity and acceleration would have different signs. So that can be determined by using the graphs, if we have the graphs. So we took a look at how we can do this algebraically, okay, an example such as a rational function, and how we can do this graphically by using the geometry of the curves. Okay. When does a projectile reach a maximum height? Suppose that an object is shot up vertically upward from a point 2 meters above the ground. We have an initial height. That initial height is absorbed into the height function right here. That is, when t is equal to 0, height would equal 2, right? This is the initial height. And it has an initial velocity of 25.5 meters per second. That is the linear coefficient, 25.5 times t. Because if you put in a value for time t, that would be in seconds, multiply seconds times meters per second, to 25.5 is meters per second, and that product would just give us meters of height. For 1 second, let's say 1 second passes, we would have an extra 25.5 meters in height beyond the initial 2 meters in height. But then there's also the effect of gravity. Okay, gravity is directing the acceleration downward, towards the center of the Earth at 4.9. That's half of 9.8 meters per second squared. Okay, so that is the correct coefficient there for this model. Right, we can find so this is a position model. Right, it tells us the position here. Position is determined as height. Right, is a position function. Okay, height is measured in meters. The time is measured in seconds. Find the velocity after 2 seconds and 4 seconds. How do you find the velocity function? Right? We need to find the velocity using the position function. So we're going to need a derivative. Okay? How do we determine when the projectile reaches its maximum height? That is when. That's the time when the projectile is at its maximum. Well, if we could imagine this trajectory, even if we could graph it, and we should be able to graph it or visualize it at the very least. What shape is this curve if we were to graph it? Right? It's a quadratic. It's a quadratic where the leading coefficient is negative 4.9. So it is a parabola that is downward facing. We call the maximum point on a downward facing parabola the vertex of the parabola. So this is asking us the question, when is it at its maximum height? We need the height model. We need to find the vertex of our parabola, therefore. We have multiple ways of finding the vertex. One way, using algebra, strictly algebra, to find the vertex of a parabola is by using the formula negative b over 2a for the quadratic function ax squared plus bx plus c. Now also using calculus in order to find the vertex. Okay, visualize this geometrically again. This is a parabola that is downward facing. It's a nice smooth polynomial curve. And the maximum would occur at a point where the tangent line would be horizontal. So we can use the derivative of this function, okay, and set that derivative equal to 0, because we know that the slope of the tangent line at the maximum height, okay, that slope of the tangent line would have to be 0. Okay. Now again, the formula for finding the input, okay, for the vertex of a parabola is negative b over 2a. right? So if we have the quadratic y equals ax squared plus bx plus c, we recall that the formula for the vertex with coordinates h, k, okay, h is equal to negative b over 2a, and then k can be found by plugging h back into the quadratic function. So k is equal to f of h, for instance, where h equals negative b over 2a. Now, we can prove that this is so by using calculus again, right? If we have a parabola that is downward facing, for instance, that's where a is less than 0, then the vertex hk would also be located where the first derivative, f prime, at the input h would have to equal 0, right? Because the slope of the tangent line here would have to equal 0. Okay, so what's the first derivative of this? F prime of x. Derivative of this with respect to x, that's where a, b, and c are constant. Derivative term by term, this is going to be a times 2x, or 2ax, plus b plus 0, right? That would be the derivative. If we then set the derivative equal to 0 and solve for x, which would be the input variable at the vertex, what do we get? Negative b divided by 2a is equal to x, verified, right? So we can algebraically determine the location of a vertex through the formula negative b over 2a. Okay? We can use calculus also in order to determine, right, the same quantity by saying, well, we know that the slope of the tangent line is 0 at the vertex of a parabola, so we could find the derivative, in this case, of our height function and set that derivative equal to 0, solve for t, and we would get the same value, okay, that we would get from negative b over 2a. Right? That would be the value of the time when the object is at its maximum height. Okay? What is the maximum height? Well, this is the height model. If you plug in the time, you would get the height. So you plug in the time at the maximum height, you get the actual maximum height. When does it hit the ground? That's at what time does the object hit the ground? So the object goes up, comes back down. It started at 2 meters in height. When does it hit the ground? And we have a model already that describes the height of this object, right? H of t. At what time does it hit the ground? That is, in other words, okay, when is the height, okay, the height equal to 0? That's when it hits the ground. So we're solving for the time when the function is equal to 0. If you get a negative value for time, you want to ignore that value because that would not be relevant in this model, right? This is only telling us the height of the object after it was shot vertically upward, not before it was shot vertically upward. So we'd only want a non-negative value for t. With what velocity does it hit the ground? Well, if we know, okay, if we know the value of t when it hits the ground, okay, that is, if the height at tg is equal to 0, okay, now we're using h here in the vertex. I'm using h here as the output, okay, to this function as well. They are not the same h as each other. Just make a note of that. Okay. This is with reference to the model that we were given in the problem. This is with reference to a formula that we learned in algebra. Okay, the height at t of g is equal to 0. Well, the velocity function, if we were to input this time, okay, that is going to tell us the velocity when it hits the ground, right? So we are going to want the velocity function now, okay, for sure, which we can find by taking the derivative of this, and plug in the value of t that we found using the height function when we set the height equal to 0, right? You set the height equal to 0 to find the time it hits the ground. You plug that time into the velocity function, which is the derivative of height, and that tells us the velocity when the object hit the ground. Okay, so some interpretation problems you have in your homework here. Okay, the output of a function, the input of a function, what is the meaning of the derivative in each case? Okay, I give you in the typed notes, we have an example or two here with some applications. I have some average rate of change going on here, instantaneous rate of change. Sometimes you're going to have to know what the formula is by carefully reading the exercise. Okay, find the average rate of change of the area of a circle. Area of a circle. You're expected to know the formula for the area of a circle then. What is the formula? The area of a circle is pi r squared. So down here, when you wanted to find the instantaneous rate of change, and then at when r is equal to 2, well, you need to take the derivative of the formula for the area of a circle with respect to r is the input variable. That's the interpretation we have in context. So we're directed to the formula that we need, okay, within the exercise. So we write out that formula, and then we're given other clues to determine what it is we're actually supposed to do. Instantaneous rate of change, that's first derivative. So we take the derivative of this. With respect to the variable r, is that we're going to plug in a value for r after we do that. Okay? There's another one. A stone is dropped into a lake, creating a circular ripple that travels outward at a speed of 60 centimeters a second. Find the rate at which the area within the circle is increasing. Rate, area, increasing. We expect the derivative of the area to be a positive quantity because it's being told to us that that's what's going to be the case. But also, just visualize this. If you drop a stone into a lake and you watch the circular ripple as it travels outward, okay, the associated area of the circle contained within that circular wave is getting larger and larger and larger. That area is increasing. We expect the derivative to therefore be a positive quantity describing that. It is a circle, right? It is a circular region. So the formula we're talking about is A of r, right? The pi r squared area of a circle. Okay. Furthermore, we're also given that we're given that the speed at which that wave is moving outward is at 60 centimeters per second. That is a change in distance with respect to time, not a change in area with respect to time, right? If it was area, that would have to be centimeters squared. This is a change in distance with respect to time. So this is a change in the radius, the distance from the wave back to the center where the stone hit the lake. Okay, so this is a change in radius with respect to time. That is a dr dt. Okay, if we were to take the derivative of this, okay, a equals pi r squared, we would be taking that derivative not with respect to r now, but instead with respect to the time variable t, as indicated here in the unit measure. The derivative of this with respect to time, okay, where radius is a function of time, therefore we would need the chain rule to do so. The derivative of this with respect to time, or implicit differentiation in other words, right? R is an implicit function of time, but we can write it as an explicit function because we're told that r of t is equal to 60 times t by this information here. So the derivative of this with respect to time is 2 pi r times dr dt by implicit differentiation, where dr dt is equal to the constant 60. Okay, the outward speed is constant at 60 centimeters per second, radius is in centimeters, time is in seconds. Okay. So you can follow along with the rest of the solution here. Right, you have similar exercises in the homework. This is about interpretation, and certainly we can engage in discussion in office hours if you feel you would like to come and talk to me about it. Okay, there's a similar problem right there. We got a volume problem right here. We got average rate of change, instantaneous rate of change. Again, read carefully. Here you're given a formula. What about here? Sodium chloride crystals are easy to grow in the shape of cubes by allowing a solution of water and sodium chloride to evaporate slowly. If V is the volume of such a cube with side length x, calculate the derivative when x equals 4. You're being told right here what the formula is. All right? The volume of a cube where the side length is x. What is the formula for the volume of a cube where the side length of that cube is x? You need that formula. That's V of x. Right, V of x, volume with respect to x, and then you're going to need to calculate the derivative of that formula with respect to x, right, because the denominator here is a unit of distance, the millimeter distance, and then you're going to input 4 into that in order to evaluate this. What's our interpretation of that? We have a derivative. That's a rate of change, an instantaneous rate of change of the output of our function. The output is volume. with respect to the input, where the input in this case represents what. Okay, so come up with the correct interpretation there. Here's current, the amount of charge, right? The quantity of charge is changing. Find the current, okay, rate of change of, okay, the amount of charge. This exercise down here uses a logistic growth model. Given information here that we can use to find out, ultimately here we're asked to find out what the values of A and B are. Okay, let's see if we can interpret this. The number of yeast cells in a laboratory culture increases rapidly initially but levels off eventually. The population is modeled by this function. Logistic growth model. These have interesting curves. Okay, they start out exponential growth, and then the rate of growth decelerates. Okay, and this approaches a carrying capacity for the environment. Okay, it's going to approach that asymptotically. You're going to be asked about that here on the next part of the question. What happens to the yeast population in the long run? Meaning, as time stretches onward, as time, the input variable, stretches onward, consider when time goes to infinity. Consider the limit as t goes to infinity to answer the question about what will happen in the long run. Okay, that's what's being implied. Okay, but back to this part, where t is measured in hours. At time t equals 0, population is 20. Stop. What is that asking us to do? Okay? This is a function that is built to tell us the size of the population. The population is modeled by this function. And then we're told if t is equal to 0, population will be 20. Okay, so that means that f of 0 must equal 20. So you plug 0 in as the value of t, and the output of this would have to equal 20. A and B are still unknown, but we're going to have some equation where the input t is 0 and the output is 20. Simplify that equation. And then we're told also at t is equal to 0. Okay? The population is increasing at a rate of 4 cells per hour. That is, when t is equal to 0, the population increases 4 cells per hour. What does that seem to indicate? We have a rate of change. Okay? A rate of change. Increasing, that means that the output of the derivative would be positive. So it's increasing at 4 cells per hour. Then the derivative of this function would have to equal positive 4 when the input is 0. If it were decreasing at a rate of 4 cells per hour, then we would want the derivative of this model to equal negative 4, because the words indicate that by saying increasing or decreasing. So this vocabulary here is suggesting to us n the units cells per hour. When the function tells us the number of cells and the input is hours, we want cells per hour. It indicates to us we want the derivative of this function. And we want the input up to that derivative to be 0. In other words, f prime of 0. And the output of that derivative will be positive 4. So f prime of 0 equals positive 4. That would give us a second equation. F of 0 equals 20 is the first one. F prime of 0 equals 4 is the second one. And with those two equations, we have a system of equations which we can solve for the values of A and B. Okay? So find the specific values of A and B, and then find out what happens to the population in the long run by the use of a limit at infinity. Okay, so it's a good combination of calculus and algebra going on here. And then a question here about Newton's law of gravitation as well. So I have another one to talk about with Newton's law of gravitation, if we'd like to take a look at that right now. Here we are, exercise 21. The force F acting on a body with mass m and velocity v is the rate of change of momentum. Remember that from the very beginning of the semester. Okay, dropping the pen to the desk, for example, that I did. Okay, the force of gravity acting on a constant mass that has a velocity v, where the velocity is changing because the acceleration, okay, is non-zero. Okay, if the mass is constant, okay, then this relationship is described by the equation F is equal to ma. Force is equal to mass times acceleration. Right? Again, because if mass is constant, okay, if mass is constant but the velocity is changing, that is, that there is an acceleration, then the derivative with respect to time of momentum, the product of mass and velocity, well, mass is constant in this example, so mass gets factored out, and we just get the derivative of velocity with respect to time, which is acceleration. So if the mass is constant, then the rate of change, the time rate of change of momentum, will be m times a, mass times acceleration. Okay? But in the theory of relativity, the mass itself varies with velocity as follows, according to this formula, where c is the speed of light. So as the velocity of a mass is approaching the speed of light c, that is, as v is approaching c from below, right, then this quantity is getting closer and closer to 1, and then this quantity in the radicand, okay, is getting closer and closer to 0 while remaining positive, because v squared over c squared would be less than 1 since v is not going to exceed c. Okay, so we have the square root of a very small number, and then the initial mass indicated by m naught, that's the mass when the velocity is 0, when the object is standing still, divided by a very small positive number, would approach, an infinite, okay, an infinite size. Right, so the mass is becoming infinitely large if the velocity of the mass, okay, of the object, approaches the speed of light. It's part of the theory of relativity. Okay, but also, if this is true, that is, notice the mass is now a function of velocity, and since velocity is a function of time, then this means that mass is now a function of time. Alright? So if we go back to this formula here, if force is the time rate of change of momentum, okay, the time rate of change of momentum, then according to the theory of relativity, this derivative would require the use of the product rule, because now both mass and velocity, they are both now functions of time. We are no longer dealing with a constant mass. Okay? Show that in that case, then, if the mass is not constant, but instead, according to theory of relativity, derived by this formula, show that instead that the time rate of change of the momentum would give us this formula instead. So translating this to our whiteboard, okay, we have again the force is the time rate of change of the momentum of an object, right, where momentum is mass times velocity, but now not only is velocity changing, but also the mass is changing with respect to velocity, and velocity is changing with respect to time. That is, we have here that mass is a function of velocity, but velocity is a function of time. So we've expressed mass as a function of time, okay, through the composition, m of v of t. So when we take now the derivative of the mass, we would need to apply the chain rule to this formula right here. And furthermore, since the mass is no longer constant, to take the derivative of the momentum, we then need the product rule. Okay, so force is the time rate of change of momentum, and that's a product of variable functions, each with respect to time. So this is equal to m times dv dt plus dm dt, okay, times v, right, by the product rule. First of all, okay, now dv dt, which we have right here, well, dv dt is the same as the acceleration function. Okay, it's a of t, and we can just call it a here in this formula. We have a is the acceleration function of time. We have v is the velocity function of time. Okay, so we have m, okay, the original mass formula, times a, the acceleration formula. Now we need to take the derivative of the mass function with respect to time. Okay, so d over dt times our formula from relativity, this right here, with respect to time. Okay, m naught over the square root of 1 minus v squared over c squared. Okay, and then that gets multiplied by v. Okay, now I'm going to replace this mass function right here, okay, by that same quantity, m naught over square root of quantity 1 minus v squared over c squared, and then that's times a. Okay, we need the derivative of this with respect to time. That requires a chain rule or implicit differentiation. M naught is constant. Okay, that is the mass when the velocity is equal to 0, so that can get factored out. Okay, so I'm going to put m naught out here. Okay, and then we have the derivative with respect to time of 1 over the square root of 1 minus v squared over c squared. I'm going to rewrite that as the quantity 1 minus v squared over c squared to the negative 1/2 power, and then take the derivative of that, right, through use of the chain rule. Okay? And then that gets multiplied by v. Okay? So we have m naught a over the square root of 1 minus v squared over c squared. Then we get plus m naught v. Let's take this derivative. Look, by chain rule, implicit differentiation, right? Negative 1/2 quantity 1 minus v squared over c squared. Power rule, we subtract 1, so to the negative 3/2 power. Now applying the chain rule, we need now the derivative of 1 minus v squared over c squared with respect to time, where v is an implicit function of time. Okay, so that derivative is, our derivative of 1 is 0, so we have negative. Okay, the c squared is constant, so that's left alone, c squared in the denominator, and v squared, derivative of that is 2v. Now we apply implicit differentiation. Okay, so we take now the derivative of v with respect to time, so a dv dt, and I moved this v here. Okay, I moved it out to the front. And again, dv dt is the acceleration function, a of t, or we'll just call that a. So we have another instance of a right here. Let's clean this up. M naught times a over the square root of 1 minus v squared over c squared plus, okay, m naught v. All these are multiplied together, right? So m naught v and a. Okay, see if we can clean this up now. All right, we've got a negative here and a negative here, so those are going to turn to a plus. We got a 2 here and a 2 here. That'll be able to cancel each other out. Okay, I've got a v right here in the numerator. I got a denominator with a c squared, and then I got all this in the denominator because of that negative exponent right there. So we have 1 minus v squared over c squared to the 3/2. Okay. So I've got this. Now I want to be able to show that this simplifies, okay, to this right here. Okay, so we have m naught times a, and then this is the quantity 1 minus v squared over c squared to the 1/2. And then here we have another m naught a, and then we also have a v squared over c squared. Then we have the quantity 1 minus v squared over c squared to the 3/2. Let's bring a common denominator now between the terms. The common denominator is going to be, right, this right here is the LCD. So on this first one, we're going to want to multiply top and bottom by what? C squared times 1 minus v squared over c squared. All right, so we have on top m naught a, okay, times c squared times 1 minus v squared over c squared. Because if we multiply 1 minus v squared over c squared, okay, times the denominator here, okay, we would get 1 minus v squared over c squared to the 3/2. Okay, and then we're just bringing along a c squared along with that. Okay, so those get combined. M naught a v squared over c squared times 1 minus v squared over c squared to the 3/2. Combine these into a single fraction, c squared times 1 minus v squared over c squared to the 3/2. I'm going to factor out m naught times a from this numerator here, right? And then, let's see here, I'm going to distribute the c squared. So I've got c squared minus v squared from this group right here, plus the v squared right here. If we can follow along there. I've distributed the c squared to these two terms. Okay, and then there's a v squared here. Right, because we have a common factor between the two fractions here in the numerator. Well then, these cancel each other out. When they cancel each other out, we're left with just a factor of c squared on top that cancels with the c squared in the denominator. Alright, we cancel those c squareds with each other. We're left with what? M naught times a, okay, over the quantity 1 minus v squared over c squared, all that to the power of 3/2. And that's what we were asked to show. F is equal to m naught a over the quantity 1 minus v squared over c squared to the power of 3/2. Okay, so this complicated exercise here brings us full circle back to the beginning of the semester when we were talking about the time rate of change of momentum being proportional to the force and in the same direction of the force that is being applied upon it. And in this case, the mass is not constant. If the mass were constant, we would just have mass times acceleration. Okay, but if the mass is not constant with respect to time, in this case, because mass is a function of velocity, and velocity is a function of time, so the mass is a function of time. Okay? Then the force is calculated by this formula instead. Now, if the velocity is not close to the speed of light, that is, if the velocity is much, much less than c, if it's a very small amount, okay, then we just have f is approximately m naught times a, okay, over what? Well, if the velocity is much less than the speed of light, okay, then this fraction right here is going to be very, very close to 0. It's going to be very small, right? We're going to have 1 minus some small fraction to the 3/2, right? And that's approximately just, okay, right? And that's approximately just the mass when the velocity is 0 times acceleration. In other words, force is equal to mass times acceleration. Okay, so this formula is really only needed when the velocity is past a certain threshold where it's sufficiently close to the speed of light, such that this would really have a noticeable effect. But it does, in fact, have an effect. Okay, and in here we have a link from the classical Newtonian physics to Einstein's theory of relativity. Okay, and that's it for this section. Let me know if you have any questions or concerns or would like to further discuss the content. Take care.